record this. Okay, so welcome. I'm one of the co-organizers. My name is Aurelien Lucchi. I'm an assistant professor at the University of Basel. And the other two co-organizers are sitting right here. So we have Frank and Hans. I think you've already heard from him. We have a bunch of other people who've been helping as well for the conference. So some of them sitting over there. So thank you, all of you. It's really a great pleasure to see so many of you here today. What I want to do for the first 15-20 minutes is just explain a little bit why we are here today, give a little bit my own perspective on the workshop. Hopefully that maybe will influence some of you also the discussions that we have outside the talks and so on. So I should mention this is an Ellis research workshop, so it's been partially funded by Ellis. Some of you will actually get some funding for travel and so on. So of course we thank them very much. The theme of the workshop is, as written here, it's between connections between stochastic calculus, statistical physics, and optimization. So our goal was to gather experts from all those fields and adjacent fields as well, to really foster collaboration. So, okay, here. So yeah, as I just said, we want foster collaboration. We hope there's a lot of discussion during the workshop. The themes I already mentioned, stochastic calculus, statistical physics, optimization, and others. I wanted to just take a little bit of time to give my own perspective. My own field of research is optimization, so one of the last one here. And specifically, I'm focusing more on the field of machine learning. And what I thought I would do is give a little bit of a recap. I guess many of you already know this, but I want to maybe give a little bit my own spin and my own perspective. So what are we trying to do in machine learning? More exactly these days in deep learning, we have a very complex model. It's a very over-parameterized sort of function, and we're trying to train the parameters of those models by optimizing some sort of loss function. So this is where optimization comes in. We usually use gradient-based methods for all sorts of reasons, efficiency, and so on. And as you already know, I guess, these methods are iterative in the sense that they start from some sort of point here, and they step in the negative direction of the gradient of the function. So the function we optimize here is f. The snabla f here is the gradient. So on the picture you're standing here, this is the gradient that is perpendicular to the level set of your function, and you take a step in this way. I always find it interesting to know this method actually technically goes back to 1847, right? So it's already been around for a long time. Of course, what we use in machine learning is a variation of it, which is the stochastic version, because we sample data, right? So what we do is that instead of using a full gradient here, we use a stochastic gradient, which is a lot cheaper. And yet this method has very nice convergence guarantees. And so again, this is something that came almost 100 years later, actually, surprisingly. So we have this kind of really pillar that is stochastic gradient descent. But what is going on in the field of machine learning these days that we tend to use slightly more advanced techniques. One of these pillar is known as the momentum technique. So there's actually different versions of it. I don't want to get too technical here. The principle is essentially, as you can see here, I highlighted these red terms, is that you're trying to, so you go in a certain direction, you take gradients in a certain direction, and then what you do is that you keep going in the same direction. So you have this little kick, right? So like here, as shown on this picture, I'm doing gradient descent, but what I try to do, so it's not very easy to see here. I realize you have gradient descent that is in red, that is kind of oscillating on this function. And then when you add this momentum, you kind of keep going in this sort of direction here, right? This is where you're going. You start here, you're trying to get to the minimum here. The momentum, as you can see, kind of pushes you towards the optimum at a faster rate. This has nice convergence guarantees, but only for convex functions or straight convex functions. But of course, in machine learning, as I will just highlight in a minute, we don't optimize convex functions. In practice, those methods still work quite well for optimizing non-convex functions. Another thing that is really boosting performance for optimizing deep networks is the choice of the step size. So we have what we call adaptive methods. I will come back to this in a few minutes. But here, so if I go back to here, right, the step size would be this term here, right? So it's by how much am I going to go in the negative direction of the gradient? And of course, you can already see on this function here, if you take it too small, you're not going to make a lot of progress. You're going to be very slow to get to your target. So this is not ideal. On the other hand, if you have something that is too high, you're going to oscillate back and forth for like here. If you oscillate back and forth, and that's also not very good because, of course, like here, if you're trying to get to this very small local minima, well, you won't be able to get there. So it's really all about choosing the right learning rate. And depending on what learning rate you choose, you can see there can be big performance gap actually between these methods. So this momentum and this choice of step size is what is used in a method called ADAM. I guess many of you have heard of it. I will come back to it, as I said, in a few minutes. But it's really where we are in the field of optimization today. I would say this is really some state-of-the-art method is to use these two techniques here. So let's move on. What are some of the interesting theoretical problems that we have in the field of machine learning? And this is the reason why all of you are here today. First of all, one thing is to understand what is in the landscape that we optimize. Right? So as I said, we have a very complex deep neural network with lots of parameters. So we have to understand what is inside this network, what is inside this landscape. One aspect of it is to understand the critical points, but there are other aspects that are interesting. If you are more familiar with optimization, you probably know that rates of convergence depend on what we call the condition number, which is essentially whether or not the level sets of your function are kind of elongated or not. And there's also an aspect that is not often discussed, actually, is the tilting of the landscape. The reason why this is important, and I guess this is again a little bit more for experts, so I'm happy to have discussions outside, is that the sort of methods that we use are not necessarily well suited for this sort of landscapes that have this sort of rotations. Some other interesting parameters is to understand, for instance, like basins of attraction, where you're trying to get to a minima, so you want to know, you want to understand what is around this sort of the sort of minima that you have in these landscapes. There's a lot of interesting questions about the trajectory of the optimizer as well. That gives a lot of information about, for instance, generalization or even different properties of the optimization method that you use. So these are some of the subsets of the theoretical questions that are of interest. Of course, the big issue we have here is, as I mentioned before, we have a lot of guarantees for convex functions, but not necessarily for non-convex functions, right? So, and non-convex functions, of course, you can have all sorts of landscapes that are very difficult to navigate. Saddle points, local minima, valleys, there's all sorts of things in there that potentially could really slow you down. So one of the questions that when we started this workshop for us was that what are the right tools that we should be using to really study these questions? One of the tools that to us at least has been quite insightful, or gave a lot of insights, is to understand stochastic gradient descent as a continuous time formulation. Right? So I'm sure a lot of speakers will discuss this, but you can, in the limit of the step size going to 0, you can reinterpret this discrete time equation as a continuous time equation. There's also some assumption you have to make on the noise here. I'm skipping a lot of details, but this, if you assume that you have some Gaussian noise here, you can turn this into a Brownian motion. So you have this differential equation here. This is very nice because we have then lots of tools that we can actually use, right? So there's Ito calculus, this Fokker-Planck equation that gives us a density, the probability density of the function we're looking for. So this is why actually this sort of tools has been quite useful in optimization. It brings a lot of all the tools that were known before, and that really lets us study the behavior of this stochastic process. There's lots of other tools. Maybe I'll just keep this slide. Yeah.
Very quickly, why everything you described depends so much on the choice of Euclidean structure?
Yes, yes.
No one ever talks about it. You're not talking about it. Why not?
Oh, there's some people talking about it. Actually, if you see right here, I actually did add differential geometry. So of the things I said can be generalized to Riemannian optimization. There's a lot.
The gradient itself depends on the choice.
Yes. So there's some work on this. I'm not talking about it here because I guess I will take a but I'm happy to discuss it offline. There's definitely work on using Riemannian optimization. I guess it's also a little bit of a question of what sort of structure do you want to use. I mean there's definitely a lot of work on this. Yeah. I'm happy to talk about it offline. And perhaps there's also more people who are more experts about this. But yes, that's definitely a good point. Yes, so some of the questions here also for us were also about the noise. So we invited also some people here who've actually worked specifically on this aspect, right? So when I told you that we go from the discrete time equations, the continuous time equation, I said we make some assumptions on the noise. Are these even the correct assumptions? If not, we can also do what we call noise injection. So we can add actually noise, right, when we optimize. Certainly some people have done this sort of thing. So I'm actually looking forward to also hear from some of you on this aspect. There's also lots of questions to me about interaction between noise and landscape, right? So we need to add the noise in a specific way, and that has to somehow take into account the specific landscape that we optimize. There's a lot of questions about algorithm design. So I told you that we use momentum or use adaptive step size. Though those sound a little bit like arbitrary choices, not completely, because they came from, people had specific insights and then did proofs of convergence to show those are good choices. But are there better algorithms we can design? And if so, how could we do that? Could we maybe leverage this continuous time formulations? Are there other ways to design efficient optimization methods? For me, actually, one important aspect is it's all about feedback. What sort of landscape are you visiting? It seems pretty clear that you have a nice convex region in your landscape. The methods we have are actually quite efficient there, because we know we even have optimal guarantees. We have lower bounds that tell us those are actually the up to constants that are actually the fastest method you could use. If you have something like this, that looks a lot more nasty. Here you would need, your algorithm would need to have this sort of knowledge and to know, okay, here I have to do something else that is not what I'm using here, right? I have to be somehow smarter. Noise, for instance, can in many cases help you to kind of go away from these sort of regions. But how? How are you supposed to do that? There's also a lot of questions about the landscape itself, as I mentioned. So we invited a lot of people here have a background in statistical physics. I think those are really people who really explore these sort of things. How do we understand what is in the landscape, right? So there's a lot of people who have studied p-spin models or other sort of models. Of course, these are not necessarily the models we have in deep learning, but how can we bridge this sort of gap here? I put some typical tools that people use here. And so for me, as someone who's interested in optimization, there's really a lot of challenges. I mentioned before that ADAM is a state of the art. It's using essentially momentum and adaptive step sizes. I think by now it has even more than 135 case stations, but it's fully on track to be the most cited paper ever, actually, which is really impressive. And still, it's for me, what is actually still very surprising is that there's no strong theoretical support for it. I mean, the proofs of convergence that we have don't really necessarily say that it's a lot faster than HTTP. So for me, that's actually quite surprising. There's a very interesting, also more empirical study by Schmidt et al. Actually, I think it's from the lab of Philip Hennig here in Tübingen, where they compare, you cannot really see here, but you can search for the reference. They compare a lot of different optimizers. And bottom line is some are better than others in some cases, but it's not like there's a very clear winner. It's not like ADAM. There's actually many different variations of ADAM, and it's not like one is always better than the other. And I put this here because I thought to me that was still rather interesting. It's essentially, I guess, a ChatGPT open version of Meta AI, and I was looking at how they actually, what is the optimizer? So they have a paragraph in the paper. And you can see it's actually for people who are theoreticians or people who are interested in theory, this to me looks a little bit like magic, right? So they're taking this ADAM W optimizer, which is a variation of ADAM. There's a certain also weight decay that they use. There's a certain learning rate. There's what they call warm up. So they first use a high learning rate, then they decay. Then there's like, you see there's all sorts of parameters. After 2000 iteration, they do this 10%. How do you even get those numbers, right? So it's like such a, I mean, I don't want to, I'm sure there's been a lot of engineering in there, and I'm sure those choices have been well justified empirically, but it's a little bit worrisome to me that we're training this set of models using some hand-based rules that we don't exactly know, if we could justify theoretically, we don't exactly know if this is always the right choice, right? So this is a little bit the state of where we are now. The results that we get if those models are amazing, but I think there's really a lot of work to be done. And that's why we wanted to have this workshop here, is to try to also get different perspectives. So try to invite different people who might have different perspectives. And that's what we hope we can engage in discussions to understand how can we improve all of this. So that was our goal. So this was a rather long introduction, giving a little bit my own perspective for why we are here today. What I want to do before we start the first speaker is just, I guess, yeah, we put a little bit more information. So I guess everyone by now should have a name tag. Just remind you also the URL of the website. If you have any questions, just come to us. So the 3 organizers are here. There's also a bunch of people who know, yeah, if you guys can raise your hand, yeah, good. So yeah, if you have questions about any sort of organization, you can just come to any of us. This is the schedule of
it's not completely up to date. Boris's talk will move back to where it was. Where's Boris? Yeah, sorry, like I sent you a mail, right? Yeah, you move back to Wednesday. And Inea will give it up here. Otherwise, it will.
It's mostly right. Yeah, we will update the.
It's a running document, and you click the link to get the current version. But I think we have converged.
And now I don't know if I'm actually ahead of time.
We have a round of everybody says who they are, what they
yes. Let me stop this recording.
And then at 10 we have again then. So yeah, let's do a quick round and then.